Hi, my name's Andrew McLaren. Today we're going to be working on some problems where we've got two boxes being pushed together. One where there's no friction. It's a little bit easier to just get the big picture on the system's thinking. And then we're going to do one with friction. This is a fairly challenging problem. It just has a couple steps to it that you have to draw out and really think about what the numbers mean. Like ChatGPT will get you the correct number here, but you're going to not understand how it did it, and it's going to be pretty confusing if you just ask some language model because they don't have the best visual processing at this time. So if you stick with me, I promise you will find it worthwhile because you'll understand this a lot better. So when we look at this problem without friction, it's fairly straightforward, but it can be somewhat confusing. So to help us out, we're going to draw a little picture where we've got our two boxes next to each other. I'm going to make the heavier one a little bit bigger. It just helps for my brain to do that. You've got your hand here that you're pushing on this box that's weighing 5 kilograms, and it is next to another box that is weighing 10 kilograms. Now we can call this box number 1 and box number 2. It will just help with keeping track of what box we're talking about. I'm going to also use our color coding as well. But we have a force that's being applied. I'm going to call that FA of 80 newtons. So the trick to this is thinking about this as one larger object where they're moving together, where you've got 1 plus 2, and that has a mass of 15 kilograms. If we're assuming that these things are moving together, then it's fairly straightforward to just do the problem. So that's a pretty big assumption here, is that these things are moving as like one object. I like to think about it as I'm a single object. So if I'm moving around, it doesn't matter how much like certain muscles are pushing on certain bones inside of me. It really is just mattering what external forces are acting on me to get me moving. Like my heart's gonna move with the rest of my body. So you don't really need to worry about internal forces. If these things are kind of moving together, you can just look at the whole mass. So if we're looking at this big picture, we can say its sum of forces is going to be equal to, in the y direction, it's got its force normal and some force gravity. Luckily, in this case, we're not having this thing going up or down at all. There's no force really being applied besides the force of gravity and the force normal. They should be complementary to each other, so that just cancels out. Whatever this number would be, that cancels out. So we're not even going to worry about doing that particular calculation as of right now. We're going to think more about the sum of forces in the x direction. Now this object, the only force that it has in the x direction is this force applied. We're doing this without friction right now. There might be some force inside between these two things, like this guy's pushing on that a little bit, and that guy's pushing on that one a little bit, but we're going to ignore that. That's something for now that is difficult to solve, so just pretend that that's not a force for a minute. That's like how much are the muscles around my heart pushing it. It doesn't really matter. We're worried about like the bigger picture body. So we're saying that this is 80 newtons in the positive direction. So the sum of forces in the x direction is also a positive 80 newtons. In other words, this force diagram is going to have some gravity pulling it down, some force normal pushing it up, but those are equal and opposite, so we don't need to worry about that. And the only force right now is going in this positive direction, and it's about 80 newtons. If we wanted to get this to scale, though, this is going to be the 15 times about 10, so it's like 150. So I really should have this green line be a little bit smaller because it's not quite that big compared to like 150-ish. Like 80 is a bit more than half. So I think that that's pretty good to scale on that force diagram. You always got to do it to scale. It's a good habit. So we can say that the sum of forces in the x direction is also equal to the mass times this acceleration in the x direction. And the total mass was 15 kilograms. And we had a sum of forces of 80 newtons, meaning this acceleration in the x direction is something that we could solve for. And it's just going to be this missing number. So what would that be? 80 divided by 15. So we get about 5.33 meters per second squared. I'm going to just put a few extra sig figs on there. We'll get rid of that when we do the rounding at the end. If I plug that back in, it sounds pretty reasonable. So we can get that acceleration value, which is one of the things that they were asking for. So we're actually going to go ahead and round that right here. So 5.3 is one of our answers right here. Now, if we want to look at the individual boxes, we can do the sum of forces for box number 1 right here. So for number 1, it was having its force of gravity pulling down a certain amount, its normal force pushing up a certain amount. They're canceling out again. But now we have this force applied in one direction, which was the 80 newtons. And I think this is only, what is that, 5 times 9.8, so it's about 50-ish. So this force applied is actually significantly bigger. Then the force gravity down, the force normal up. So this is force of gravity on 1, force normal on 1. And then we have this other force now that's being applied. It's in between these two. So I'm going to call this the force of 2 on 1. It is some mystery number, but we're trying to solve for that. We're trying to figure out what that force is between these two objects. So if we were to look at the sum of forces for the x direction for box 1, it is going to be this force applied to the whole system as well as just applied to 1, plus the force of box 2 on 1. Because there's some contact between those two things, that box has to be pushing back on it just a little bit at least. And we can look at the sum of forces for box 1 by looking at its mass 1 times the acceleration, which is the same as this other acceleration. If these things are moving together as a system, then they should be having the same acceleration value. So we can say that the acceleration here is also a positive 5.33. I'm going to use the 5.3 number because we rounded to that, though if we want the numbers to work out exactly, we should use the unrounded. Just sometimes the sig figs can get thrown off if you round too early. But because we report that acceleration, I'm going to use that. So that's the acceleration that we're experiencing right now for object 1. Object 1 we had said was 5 kilograms. So if we take that times that by 5, we're getting 26.6-ish. Also, I'm just seeing, yeah, it's a slightly different number. They end up rounding out about the same if you were to use the rounded or unrounded number. I'm going to follow the strict sig fig rules, which is use your reported number before. So we can say that the sum of forces for object 1 is going to have that 26.5 value for like the total. We've got the 26.5 when we add up these two numbers, and we had 80 newtons being applied in the positive direction, which means there's this other number, which is some sort of negative number that we're applying in here. So you can do a little math rearrange for that if you'd like, but you can also plug it in and see what's appropriate. So if we have 26.5 and we subtract 80 from that, we get a negative 53.5 newtons. So this kind of makes sense because it's in the opposite direction of the other force. So we're saying this is negative 53.5 newtons. If we want to round that to the 2 sig figs, that's going to be a negative of 54 newtons. And yeah, actually, if you'd use the 0.6 here, then this would actually round down to 53. So it's coming in where if you look at the rounded number versus unrounded, it's a slightly different number, but it's within +1 or -1 of it. So within sig figs, that's okay. You don't want to be off by like a bigger factor, but that's all right. And just to kind of reinforce this, we can also look at box number 2. Its sum of forces for box number 2 is going to be, now we don't have any force applied being directly done to that. It is just this force 1 on 2 now. So whatever this was pushing on that with, that will also push the other way, equal and opposite forces, right? So if we're talking about this, now the only force is 1 on 2. We had said that this is going to be now a positive 54 newtons, meaning that our sum of forces in the x direction for box 2 is positive 54 newtons. We can look at the force diagram for number 2 as well in a similar regard. But now number 2 is just having this force being applied in the positive direction. There's no force friction. This is just how much the other box is pushing it forward. And this was like around 100, so I'm gonna make the force applied be a little bit smaller for that diagram. So we've only got the force of box 1 on 2, which is now a positive 54 newtons. We can double check that by looking at the sum of forces in the x direction being equal to the mass. In the situation, we're talking about mass 2 times the acceleration in this x direction for mass 2. So mass 2 was going to be 10 kilograms. And we'd said that it was experiencing an acceleration that was the same as the other ones. It's at 5.4. Or 5.3 meters per second squared, plus or minus 1. That's totally fine. So this looks like, yes, it is going to be about that 53 or 54 number, depending on if you're rounding earlier or not. So we've got math that seems to be mathing correctly when we double check it. Physics can be a little bit tricky because if it's plus or minus 1 on that last sig fig, it's okay, but you don't want to have it being much more than that. It's just kind of a tricky part about sig figs. So yeah, that's the big picture without friction. Take some time to really think through it and double check it. So imagine what the friction problem's going to be like. Yeah, get ready. So to start us off, a little diagram here looks similar to the last problem, but it is a little bit different. Due to us now working with some force friction, we're going to need to actually solve for these forces of gravity and normal force. So due to that, I'm going to put some more labels on this. If we're talking about 1 plus 2 as a system, we're going to want to have that label on our formulas. So this guy right here, I'm going to do a little color coding. The force normal for the object 1 plus 2 is going to be useful because we're just thinking about this larger orange box, which is a combination of these two boxes put together. If you're not sure about that, I did go over it in the previous problem quite a bit, so make sure you've watched that part. Now, this force gravity on this larger object is going to be appropriate for its how much mass there is. So the force of gravity here is just that negative 9.8 meters per second squared times the mass. So we've got the 15 kilograms mass here. So this is just the force of gravity being mass times the acceleration constant g. But I usually think of this as a negative number, and the acceleration is a negative number. So the force would also be a negative number. So we get that 15 times that 9.8. But again, this is a negative 147 newtons. So the force of gravity of 1 plus 2 is equal to this negative 147 newtons, meaning the force normal, because these have to be equal and opposite, this object is not moving up or down, is going to be a positive 147 newtons. And we can then think about, well, what is my force of friction that would be appropriate with that? And we really want to think about, is this static or potentially kinematic? So if we're assuming it is static, we can check to see if that actually holds true or not, and work with that number. So we can look at the force of friction here, and it's going to be some number. I'm not sure exactly how big it is right now, but this is that force applied, which was the positive 80 newtons. If we look at the force friction here, you can get that from this coefficient of friction formula. But actually, you know what? Real quick, let's just write out the sum of forces in the x direction, 1 plus 2. So for this larger object, there's a force that's being applied, and there's some friction for this larger thing as well. So there is definitely an F applied plus the force of friction for objects 1 plus 2. And we're saying that, well, we want to know if this thing can accelerate. So is there a sum of forces that makes sense here? When we look at the coefficient of friction, that was, I believe, 0.5 was the value that we've given you for this problem. The floor and the boxes, yeah. So it's 0.5, meaning that would be the force of friction over the normal force. I usually write it in this format and keep it like that. In this case, the force normal is 147 newtons. And this is the force normal of objects 1 plus 2. And that will help us get the force of friction that's appropriate as well with that. So if that was 147, we just kind of cut that number in half to get the force friction. AKA we're just timesing by 0.5 to get that. I like to write this out in this format because it's pretty apparent that that is one half when you write it out like that. It's easy to mess up the numbers in that stage, so I would encourage you to write it out in that format. So the force friction here, the static, is looking like we're getting, when we do the calculation, it's giving us a positive value, but I'm recognizing it's going in this direction. What I'm getting right there is a negative 73.5. So if we're getting negative 73.5 newtons for this force friction, and the applied was 80 newtons, then we're getting some sort of positive value here, which means that there's going to be some sort of acceleration, because the mass of these objects, 1 plus 2 times the acceleration in the x direction for objects 1 plus 2, whatever this is, it's some sort of positive number. This is not 0, which is an issue because we were saying that this thing's static. If it's accelerating, then this is definitely sliding. And so we're having an issue here. I'm not even going to calculate the value. It's going to be like, what is that? 7-ish. So that would mean the acceleration is not 0 as well. So we've got an issue. No. So this is actually going to be kinematic friction. So we can use some of the math we did earlier because the gravity is still pulling down the same amount. The force normal is still going up the same amount, but we're going to need to think about this force diagram as the kinematic version of this. And when we do that, we're getting a slightly different value. So we had done the static here. This was the value that just didn't really work out. Usually the kinematic friction is a little bit less. Sometimes it's a fair amount less. Things that are still kind of stick to each other better than things that are sliding over generally. So if we look at this, we need to get rid of that 0.5. The kinematic value that I believe that I gave you was 0.4. And that means that we're getting a slightly different value. Yeah, so it's 0.4 for the coefficient of friction here. So we have a value of 147 times 0.4, and we get 50, okay, right, 58.8 newtons for the force friction. That's kinematic. Because this is going in the opposite direction, we're going to think of that as a negative 58.8 newtons. It's opposing this applied force. So this object is accelerating in one direction. The friction's like, hey, hold on, slow down. I like to think about what would happen if we got rid of the friction. It would just go really, really quick. The friction's slowing it down, so it's kind of canceling out that force applied. So if we want to think about our sum of forces now, when we actually have this with the kinematic equation, we get some values that actually are more appropriate. So we get a negative 58.8 newtons for that force friction due to it going to the left. And then we're going to add that to the 80 newtons going the other way. So our sum of forces looks like it's still going in the positive direction, so it is accelerating. That kind of makes sense. So if we have 80 minus that 58.8 newtons, we're going to get a value of 21.2 newtons. I do believe we were supposed to report out the force of friction. So if we wanted to do the technical sig fig rules, this should be reported out as 59 newtons. I'm going to say that this is accurate to multiple sig figs. I just wrote it as one. So let's say it's 0.40, just to make sure we're not getting covered up too much with that level of imprecision in that constant I gave you. So let's say it's about 59 newtons. It's close. So this is actually 21 newtons going in that positive direction. So if we want to then look at the sum of forces for these two, we can relate that to the mass of the two objects times this acceleration in the x direction. We could label that as this, but the two objects are moving together, which means each individual acceleration also matches this. So we could just call it the acceleration in the x direction, get rid of that label. I'm going to keep it for now, though, because it's just good to have some clarity with what numbers we're talking about and why at this point. So if we're saying that this is 21 newtons in the positive direction, and we have a mass of, I believe it was 15 kilograms, because the two were 5 and 10 kilograms, so together they're 15 kilograms. We can then solve for this acceleration value. If we take the 21, we divide that by 15, we're getting a value of 1.4 meters per second squared in the positive direction. So this is pretty useful. We've got our acceleration value, as well as that force of friction, which was asked for. And now if you want to know what's going on between these two objects, one of them is pushing a bit on that, and that's pushing a bit on that. And we can actually solve for that using the force diagram for 1 or 2. 2 is a bit easier, you could say, because it's just got one object on there. So number 2, or 1, it's not got the force applied and this other thing in friction, it's got less forces involved in it. So for object 2, there is some sort of force of gravity down. There's some sort of normal force up. Those being equal and opposite to each other is going to be somewhat important. But this is for object 2. So we're just going to put those labels on there. There is going to also be a slight force of object 1 on 2, kind of pushing it forward a little bit. And there's going to be some friction as well. So this is the friction for object 2. I'm not exactly sure how big these are compared to those. We'll get that figured out in a little bit, but we do know that this force going here is a little bit greater than that because this object is accelerating in that direction. So for object 2, it really has not the force applied being applied directly to it anymore, because that's hitting box 1, which then pushes box 2. So it's just got some gravity pulling down, normal force preventing it from falling downward, and some friction holding it back so it doesn't accelerate quite as fast as what we saw in the previous problem, but it is definitely accelerating. So if we look at the force of gravity on object 2, it's the mass of object 2 times the acceleration of gravity. So object 2 was 10 kilograms, and the acceleration of gravity is 9.8 meters per second squared. So we put those together, we get negative 98 newtons for this number, meaning the force normal that's countering that to prevent this object from falling through the table is going to be a positive 98 newtons. And we can now look at the sum of forces in the x direction. The sum of forces in the y was 0. It's just these two numbers canceling out. For object 2, just keeping my labels on there. Now, sum of forces in the x direction is going to be the force of 1 on 2 plus some sort of force of friction for object 2. This is different than the force of friction of 1 and 2 because now we're looking at a smaller object. The gravity is less, the force normal is less, so it's experiencing a little bit less friction than that larger system that we were thinking about just a minute ago. Really important to have good labels. So if we wanted to calculate the force friction, we do have this coefficient for the kinetic friction. And this is all over that force normal for object 2. We had this value as 0.4, and the force normal was 98 newtons here. Kind of coming from that force diagram up above. Do a little calculator work, keeping it arranged how I like it is just how my brain does these. Okay, so our value that we're getting here is 39.2 for force friction. And in this case, it is also a negative number because it's going to the left. So we've got a negative 39.2 newtons going one way. And we have this mystery number, force of 1 on 2. We're solving for that. and that is going to be equal to the sum of forces in the x direction. We could actually solve for the sum of forces in the x direction because it is related to the actual acceleration in this x direction, which is the same value. Seeing how these boxes are moving together, it's the same value as above, like they're accelerating together. So we have a positive 1.4 meters per second squared being multiplied by its mass of 10 kilograms. Just double checking that object 2, yeah, was the 10 kilogram mass. Always good to double check that. So to save you some time, I made a little mental mistake in my math, doing 140 as opposed to 14. I was able to realize that was incorrect because I was looking at this other object and the force was just way too big. Like this thing should be accelerating that way, not having a deceleration from this lower force. So saving you a little bit of time on that. If you need an explanation about what I'm talking about there, please leave a comment. I'm happy to talk more about why that I knew that that answer was incorrect. So if we're actually working with a value of 14 newtons and not 140, this force is a lot less big than what I had initially thought when I was doing this problem. If we're working with the 14 and we're adding an appropriate number from that force friction here, the force 1 on 2 is actually about 53.2. So we're getting a value of 53.2 newtons. In this case, that is what's pushing object to the side. So that's that guy right there. So we've got 53.2 for the force of object 1 on 2. And that seems to be a much more appropriate number to give us the relative amount of force that we need for object number 2. Now, if we look at object number 1, we do have a force of gravity that is pulling it down, force of gravity on object 1, force of normal on object 1. These should be equal and opposite because object 1 is not flying up or dropping down. And we can say that this force of gravity is just the mass times acceleration of gravity, and this is for object 1, which had 5 kilograms for its mass. It was going to, without anything else, fall at this acceleration, but there's a table holding it up, so that's not going to really be the case. But we can get the newtons at least. 5 times 9.8 newtons, we get 49 newtons down for that force gravity, meaning the force normal is a positive 49 newtons. For object 1, we do have a couple different forces acting on it. We've got this applied force, as well as some friction, and the other box pushing on it. So this applied force, which was 80 newtons, I'm going to make that a bit bigger than these other ones, which were only 50. Trying to keep this proportional helps you double check the problems like what I saw just a minute ago. We do have some force friction, which is going to be a little bit less than half of what we've got there. And then we've got some force now of object 2 on 1. Because we're talking about object 1, box 2 is pushing back on it a little bit. And just kind of knowing the math, I think that'll be a bit bigger than the force friction. But that could be hard to know at this point if you were trying to solve for this without doing box 2 and just going straight to here. Though it is definitely doable. If we're looking at the coefficient of friction for object 1, you've got that force normal of object 1 and force friction now kinematic of object 1. That was our 49 newtons that we have for its how much it's being held up. And the kinematic friction is going to be an appropriate value. We said that the constant here was 0.4. So that force friction is 0.4 times 49. we're getting a value of 19.6 newtons for our force friction. If we're looking at these sum of forces in the x direction for 1, I'm just going to rewrite this out with the force applied plus force friction kinematic for object 1 plus the force of 2 on 1. Just give you a little bit of colors to help your brain, because we are not machines. It just helps to have some visuals to go along with, like, where did that number come from. And we know that this was the 80 newtons that was being applied. We've also got that kinematic friction value that we just solved for. That should be going the other direction. So I would put that in as a negative 19.6 newtons. And we can actually solve for this using a value for the sum of forces in the x direction, because it is the mass of object 1 times acceleration in this x direction for object 1, which should be the same as the overall acceleration value that we have for this problem. We can go ahead and just plug them in and double check. For object 1, we'd said this was 5 kilograms. And the overall acceleration that we're experiencing here for both objects is 1.4 meters per second squared. So we multiply those together, we get the sum of forces value for object 1. Okay, that's 7, nice and even. Okay. We've got 7 as our sum of forces value. And we can then sum these up and see what our force of 2 on 1 should be. So we've got, what is that, 7 minus 80 plus 19.6. Yeah, we're getting a negative 53.4 newtons for how much this is pushing back. Which we can round as the negative 54 newtons. So if we look at this, it is close. These numbers are slightly off because we're rounding only to 2 sig figs. Being off by plus or minus 1 here is very reasonable. Just because we're limiting it to 2 sig figs. Really, when you have like 53 written, this is assuming that the last number is off by just a little bit, but not much. So this is effectively the same as this number when we write it out with just 2 sig figs. So that is perfectly acceptable to me. And we can see that these numbers are negative and negative, but they're not quite enough to cancel out that positive in the positive direction, meaning we do have a sum of positive 7. You can also just add those two negatives up together and see that that's 7 less than 80, I believe. So we got the 53.4 is a negative number. We're adding to that a negative 19.6. Yeah, and that works out when you look at those together as negatives. Okay, so that's another way of solving this problem. I would look at this with both object 1 and 2. It just helps you reinforce that you have the correct numbers. If you had used just the raw numbers without any rounding, you're going to get the exact same value here, though the level of precision would be not really implied. The math, it just works better when you just do the numbers. So yeah, I think that's it. Thank you for joining me.